we know that the compact car in the previous problem was moving at 115 kilometers per hour east, so we'll make the VI equal to that. But we need to work in meters per second, so you do your conversion. You get 31.9 meters per second for the VI of the car. He hits the brakes for 2 seconds, so the time of the braking is 2 seconds, and the force applied by the brakes is 5,000 newtons. Now, the car's velocity is initially positive, and he hits the brakes. That means the force applied is negative. So it's a negative force. Now, part A, what is the change in momentum? That is the direct magnitude and direction of the impulse. So let's use our impulse momentum theorem. And so the force is negative 5,000, and the time is 2. And you see the question says, what is the change in momentum? In other words, what is the impulse? So really all you need to do is get this product. And so the impulse is negative 10,000 newton seconds. So that's the answer to A. Now B says, what is the velocity of the car after the braking is done for 2 seconds? So now we'll go back to using this equation. So now it's negative 10,000, which is the change in momentum, equals the car's mass, which was 725 kilograms. Its final velocity is what we want to know. And from that you subtract the initial momentum, 725 times 31.9. And then you solve and you get 18 meters per second for VF. Okay, so since we had a negative momentum change, the velocity decreases. All right, so number 3, we got a 7-kilogram bowling ball rolling down an alley. Its velocity, VI, is 2 meters per second. For each impulse shown in the figure, what is the speed and direction of the motion of the ball? So the VI is 2. Now, the first example shows us we have a graph looking like this, where this is 5, 0, negative 5, you got 1 and 2, and you got this. So basically you have, this is force over here, this is time here. So you have a force of 5 newtons applied for 1 second. So that means that you have an impulse of 5 newton seconds, right? F times t. Right? F delta t, 5 times 1 is 5. So therefore, for the first one, Ft mvf minus mvi. So you have 5 equals the ball's mass, which is 7. You want to know what is its velocity after that change in momentum. So after this force was applied for a second, minus 7 times the initial velocity, 2. And so you solve that and get 2.7 meters per second. And then for part B, instead of the graph looking like that, it's flipped on the x-axis. So this is your graph. So now the impulse is negative 5. So now negative 5 equals 7 times VF minus 7 times 2. And so if you gave a negative change in momentum, you would expect that the velocity would decrease, and it does, to 1.3 meters per second. From here, right, we know that that's a height of 1.20 meters. Right, so the ball starts with the velocity VI of 0. It falls at the rate of g, and it hits the chalk tray. Right, so it'll have some VF when it gets down here. Okay, the VF we could find by doing our kinematics. So VF squared, VI squared 2g delta d. So the VI is 0, 2, negative 9.8, and 1.2. You get that, you get 4.85 meters per second. Remember, you're doing a square root, so it's plus or minus, and the ball is traveling down. So you got to put the negative on there. So then the speed, or the velocity at which it hits the chalk tray is negative 4.85 meters per second. So it hits, and now there's an impulse, because the chalk tray applies a force upwards. And now the ball changes direction, and it goes up. Okay? So the impulse happens here, right, on the chalk tray. So we'll say that that's the impulse, and we know to find impulse, Ft mvf minus mvi. Now the vi, right, the velocity with which the ball approached it was negative 4.85, so that's going to be your vi. Your vf is going to be found by how high the ball rises. So now the ball leaves. So it leaves with some velocity, vi, and it rises up to a height here of 0.700 meters, and at the maximum height, the VF is 0. So now you could find the VI, which is the VF for this equation, but we'll get the VI. So VF squared is VI squared 2G delta D. Now the VF is 0, so 0 is VI squared 2G delta D. Your delta D is 0.7, so you solve for your VI, and you got 3.7 meters per second. 3.7. So it approaches the chalk tray at negative 4.85, and it leaves at 3.7. So then you can put that in this equation to figure out the change in momentum, or the impulse. So Ft, mass of the ball is 0.5, times the final, which is 3.7, minus 0.5 times the initial, which is negative 4.85. And then you put those in, and you get 4.3 Newton seconds to be the impulse, the change in momentum. So the key really was making sure this is negative, because it was, right, the ball changes direction, so that's really important that you have a negative there.